So in that first video, we really just sort of discussed polynomials in general. In the next videos, we'll get into some actual types of problems you'll end up seeing in Delta Math and on the closure and such. So to begin with, let's talk a little bit more about end behavior. Now, if we are given a general polynomial, p of x equals something like this, notice that at large values of x, so in this case, I'm kind of thinking about x going to infinity, so like a billion, a million, that kind of stuff. This here is really going to overwhelm all of the other ones because a really big number raised to a power of n is just a giant number compared to the other ones. So this term actually overpowers the other terms. Only when we're at very large values of x, though. Or at large negative values. That doesn't really make sense because a large negative value is sort of the opposite direction. But what I'm saying here is as x goes to negative infinity. That term just sort of overpowers it. So this leads us to another fact about end behavior. The end behavior of a polynomial is determined by its leading term. Which looks like this. So this is a really key point that we're going to be using throughout this section. In order to find the end behavior of a polynomial, it's determined by whatever its leading term is. So what I like to do at this point is kind of draw a little table to illustrate this. You might want to put this in your notes somewhere. And up here we're going to write the leading coefficient. And over here we're going to say degree. So for the leading coefficient, that's a sub n, if it's positive or negative is going to play a role. And then for the degree, if n is even or if n is odd, that's going to play a role. So basically, here's the idea. I don't care about the middle, but the end behavior, if the leading term is positive and n is even, is going to look like this. We'll go ahead and draw some axes in here for each of them. If if the leading coefficient is negative and n is even, then it looks like this. It reflects over the x-axis. For odd and positive, it does this. And then for negative and positive, it flips over the x-axis or the y-axis. And so we end up with this. Now, this is just a visual. Obviously, this is not how you should answer the question because you still have to use the correct notation as x goes to infinity, y goes to whatever. But this is just a really good visual moving forward. This is something you probably want to have in your notes to refer to. Now let's jump straight into an example. So let's just say we'll do a couple of these. Determine the end behavior of the following. So for the first one, let's do p of x equals negative 5x to the power of 7 plus 3x to the power of 5 minus 18x to the fourth plus 3x. All right, so all we really need in this polynomial is the leading term. So let's take a look here. The largest exponent is right here, it's 7, and then 5, 4, and this is technically a 1. There's a 1 there, but it's still smaller than 7. So the leading term is actually going to be that first one I wrote. This polynomial was already in standard form. So this is the leading term. And so that means that I have my coefficient is a sub 7 and it's a negative number, and my degree n, the degree actually equals 7 in this case. So it's odd. So just to note, this is negative and this one is odd. So let's consult our table. We're in the negative odd, so that is in the bottom right corner of my table. So that means that the end behavior is going to look something like this. Or the graph will look something like this, I should say. At its edges, it's going to go like that. I don't really care what happens in the middle, and then on the other side, it's going to do that. And so our final answer is we would just say, well, if you wanted to kind of first do the English version, you could say it rises left. And so that would be as x goes to the left, the y values rise forever. And it falls to the right, so that means as x goes to the right, the y values decrease forever. I do expect your answer to be in this format. However, if you write it as rises left and falls right, you'll probably earn quite a few of the points, but in order to get full points, you really need to use the correct notation. And that's it. That's all this problem is saying. What is the end behavior? Oh, it rises left and it falls right. I guess I could put an S there. And that would be it. Now, we will see some that start to get a little bit trickier, but nothing too much more complicated than this. Let's try another one, one that I might use to try to confuse you. Let's use a different letter. We've already used P. Let's say I had a polynomial negative 10 minus 33x to the 8th plus 17x to the 32 minus 12x to the 17 plus 73x to the 28. Now the reason this one might be confusing is because it's not in standard form. So you'd actually have to look to find the largest exponent. It looks to me like it will be this one. So this in standard form would actually be the leading term. So if we were, you don't have to rewrite it, but if we were to do so, you would do something like this. Right, so this is now in standard form. We have the largest exponent first and the rest are all lower than it. So our leading term is 17x to the 32. You'll notice that the leading coefficient is positive and the degree is even. So if we look back at our table, we're in the top left corner, positive and even. So that tells me that the graph will do something like this. It's going to rise left and also rise right. And so then the final answer I would write in the correct notation would be as x goes to negative infinity, meaning I'm going to the left, y is going to rise, meaning y goes to infinity. And as x goes to positive infinity, so that's saying as I go to the right, y rises, so y is going to positive infinity. And that would be my final answer. So that concludes our discussion on end behavior. In the next videos, we'll talk more about what happens in the middle region, and specifically that will be finding the zeros or x-intercepts of a polynomial.